Starting from this lecture, we're gonna start to work on the so-called message passing interface library. But before we talk about MPI, I want to just review a little bit about the paracomputer cluster architecture. Um, I actually had two videos. I have actually two videos, two YouTube videos, in which I talked about how a common computer cluster is actually set up. Um, So in the first video, I talked about how to build your own computer cluster at home by using spare parts, by using spare desktop computers. And in the second video, I talked about how to actually improve the computer cluster's performance by using a high-performance shared parallel file system and using cables instead of wireless routers. So what exactly is a computer cluster, right? It's it's not really that difficult to understand. It's basically just a bunch of ordinary common desktop computers connected using switches and cables, Ethernet cables, basically. And it has a shared file system, so every computer or every computing node that's connected to the network can have the same view to the same file system. So every computer node um, can have a view to the shared file system, so they can access files. And the different computers or different nodes can talk with each other, can communicate or passing information to each other by 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 using the Ethernet cable, right? Or the wireless network. It's depending upon what's actually the connection technology you use to connect all those computers. So it's basically just a bunch of computers connected together, right, with a shared file system, and they can talk to each other. They can pass information. They can communicate to each other by using the cable. Right? You can set up this kind of a paracomputer cluster by using just a commodity hardware. It's not really that difficult to do by yourself. Right? And then we're faced with the second problem. How do we actually program a computer cluster? Right? Programming a computer cluster is kind of different from programming a single desktop or a single computer. The reason is that for now you have to actually account for the different different computing nodes in your cluster. Right? You are writing program not to run just on a single desktop or a single laptop or a single node. You are writing computer program that's gonna run on all those computers that's connected through a network. So how do you actually do that, right? Um, how do you actually write computer programs that can run on a cluster, right? A naive option might be just to write different source code for different node. Is that going to work, right? Is that going to work? Is that a good strategy for programming a collection of a potentially large collection of computers, right? Is that a reasonable strategy? So if you actually write a separate source code for every different node on your cluster, what might be the consequences, right? If you think about it, what might be possible consequences, right? So first of all, if you just have a very small cluster with like a few nodes, writing separate source code for each of the node is not too big a problem, right? Uh, but in practice, in reality, many of those big simulation programs actually run on huge clusters. Those supercomputers have actually uh, millions and millions of computing nodes. So if you actually try to actually write a separate source code for each of the different nodes, you're going to have too many source codes. And it will become very quickly a nightmare to actually just maintain and to actually manage all those source code. That's one of the problems. That's one of the direct consequences we can actually think of if you actually choose this particular strategy, right? Write a different source code for different nodes, right? Another thing that you will soon discover is that you will have lots of code duplications, right? Why do we have code duplications? The reason is because many times we have actually a kind of a programming scenario in which different nodes or different cores or different kind of computer processes actually just handles a different portion of the data, but the operations that you're going to apply on those different portions of the data are pretty much the same. So the logic that's going to be applied on those data are pretty much identical, right? You're just dealing with different kinds of data or different portions of data, but the logic is pretty much the same, which means that you're going to have code duplications if you decide to actually write different source code for different nodes. You're going to have lots of code duplications. All those different nodes are basically just running the same logic, right? The only thing that's different is just the range of the data, basically, right? And in this kind of case, you're going to have lots of code duplication, right? If you want to change one part of the code, you have to change every other codes, right? Again, this is a very poor, very bad for code management, right? And a third problem with this kind of choice is that data transfer. Don't forget the when you actually run your code on a cluster of computers with many nodes, it's sometimes inevitable to actually transfer data among those nodes, right? How do you actually transfer data if you're actually writing separate source codes for different nodes, right? If all those source codes are actually independent to each other, how do you actually refer to the other source code, the other node within one source code? There are strategies for doing that. For example, if you actually use HTTP, this kind of a protocol, right? But in a closely coupled computer cluster, doing that kind of thing could have a very high overhead. You might not be able to actually take advantage of the very fast communication among all those different computer clusters, right? Among all those different computer nodes. So data transfer, you could actually introduce unnecessary complexity into the data transfer layer, right? And there are also other kinds of difficulties if you choose to go down this particular path, right? So what might be the alternative, right? What might be the alternative? How can we actually program a computer cluster without writing separate source codes for different nodes, right? So what do we want to achieve? The basic goal we want to achieve is that we can write a single set of source code, and this single set of source code is going to run on all the nodes. That's what we want to achieve. We don't want to write a separate source code for different nodes. We want to just write one source code, and this one piece of source code is going to be viewed and be executed by all those different nodes on the computer cluster, right? So if we actually pick this kind of a path, what might be the difficulties, right? What might be the difficulties? One immediate difficulty is that how do we actually distribute the workload? How to distribute the workload? How can we actually partition the entire workload so that each of the node will execute just a portion of it, right? All the nodes are looking at exactly the same source code. So how can we actually distribute the workload? Isn't that something that we have to sort of solve? Isn't that a problem that we have to solve, right? Because every node is actually looking at is going to be executing exactly the same set of source codes. So how do we actually partition work among all those different nodes, right? So how do we actually do that? Is has a, it actually has quite a few solutions, right? But the solution that we are going to talk about, in particular the solution that's implemented by the message passing interface library, the Mpi library, is actually quite ingenious. It's actually quite ingenious, right? So in order to actually distribute the workload, you must have a mechanism to distinguish different computer nodes inside of the cluster, inside of this network, right? So if you have an ID, if you have a unique ID for all those different nodes, then inside of your source code, you can write your codes targeting towards one or a range of those IDs, right? So you need a mechanism to distribute IDs, to distribute unique IDs to all those different nodes in the cluster. That's the first thing that we are going to need, right? An ID. A second thing is that we must have the capability to write different logic for different node ID uh, inside of the same source code, right? The second problem is actually easier than you can imagine, because in most of the modern programming languages, you have a branching structure that allows you to actually uh, select a block of codes, or select a certain execution path based upon certain conditions. If you have a unique ID for different nodes, then those ID can be used to actually set up your branching conditions. Then different set of nodes or different set of IDs can actually take different paths of execution, right? The first part, how do you actually assign a unique ID to each of the different nodes? This part might not be actually as straightforward as uh, we can imagine, right? But we don't have to solve this problem. The message passing interface, the MPI library, actually has already solved this problem for us. It has solved the problem for us. So for the message passing interface, MPI, we have a conceptual diagram. We have a conceptual diagram that just looks like that. It just looks like. So on the right hand side, we have a computer cluster, which is composed of lots of different nodes, right? On some of the nodes, you have just one CPU core, but on other nodes, you could have like multiple CPU cores, right? So those are your hardware. Those are your computing hardware, and a cluster is like connected by different by the network. And inside of the MPI programming paradigm, you have something that's called a communicator. So the biggest communicator in any MPI program is called MPI world. That's the biggest communicator. What exactly is a communicator? A communicator is basically just a collection of IDs. So the biggest communicator is called world, and inside of this communicator, you have different IDs. You can sort of see 0, 1, 2, 3, 4. You have all those different IDs, and those IDs have a here we are introducing a terminology here. It's called a rank. It's called a rank. All those IDs are called ranks, and all those IDs correspond to those different computing hardware, right? So for example, the rank 0, the ID 0 is assigned to CPU 0 on node 01. Rank 1 is assigned to CPU 1 on node 01, right? And then rank 2 is assigned to CPU 0 on node 02. And this kind of setup, this kind of a correspondence between a unique ID and a computing hardware, like a CPU core, this kind of correspondence has already been established for you inside of the MPI library. And all we have to do is to be able to actually utilize this kind of capability, this kind of setup in our programming, in our pair program. So now let's try to for now all those concepts are quite abstract. But now let's take a look at one specific example, and I will try to actually make it easier to understand. How do we actually map this kind of abstract concept into a concrete program? So let me try to describe the problem we're trying to solve. So in this first example, we're going to do a parallel summation. We're going to do a parallel summation of a bunch of numbers that's distributed in different files. So here I'm actually in my terminal. If I do a AOS to list all the files, I can see like 8 files. I have 8 files from file.0 to file.7. I got like 8 different files. And inside each file, there's a sequence of numbers. So if I do a cat of file.0, I can see in the first file I got like 3 numbers. 3 numbers. All of them are actually floating point numbers. And then if I do cat file.7, I'm gonna have a lot more numbers, some more numbers. what I want to do is to do a summation. To do a summation of all those numbers that's distributed among all those different files. Right. For this kind of simple problem, I don't really have to use a pair program to actually do the summation. I can just sum all those numbers together by using a shell script, right? By using a shell script. Suppose I do a cat file dot star, and then I pipe it through awk, right? Awk s plus equals to the first column, right? And then end, and then print s, and it's gonna tell me the summation is 83.7143. That's all the numbers that's summed together, right? But this script is a sequential program basically. It's basically a sequential program. What I want to do is to actually, um, for my computer, the computer that I'm using right now, it has 8 different cores. It has 8 different cores. It's a So what I want to do is to, for each of the core, to do a partial summation for the numbers in each of the files, right? And once the partial summation is done, I want each core to write a separate output file that's gonna write out the partial summation that has already been done by that particular core. So for now, there are how many each of the file is gonna have a different number of numbers. It's gonna have a different different set of numbers. What I want to do is to have a parallel program that's gonna read all those different files. That's gonna read all those different files, and each core is gonna read a different file. And then each core is going to do a summation for all those numbers in its own file. And then each core is going to write out a different output file. And inside of that output file, there's one number that's the summation of all the numbers in its corresponding input file. So how can I do that, right? How can I do that? By using the message passing library, by using the Mpi library. So what I'm going to do, I'm going to write a source code using Emacs, and then I'm gonna call my source code sumpar.cpp. So I'm doing a C++ program. The Mpi library exists not just for C++, but also exists for Fortran, for C, and for every major variations of a main language, a mainstream language. It also has ports to Python. It also has ports to different kinds of computer languages. But here I'm just using the C++ language to write my source code. So I'm inside my editor now. So what I'm gonna do? I'm gonna write a computer program, basically a C++ program that's gonna use the Mpi library, right? So before I actually write the main function, I need to include some of the headers, right? So for C++, I'm gonna use stdc++.h. I'm gonna include this particular header. The reason I'm including this particular header file is because inside of this particular header, it's actually including almost every other headers in the C++ language. So by including this particular header, I am pretty much including all the different headers provided by the C++ language. It's not really a good practice, but it's useful for beginners if you cannot figure out which kind of functionality actually exists in which header files, right? You can just include all those header files without actually thinking too much. But later on, when we actually try to improve the efficiencies or try to improve the organization of the codes, we're gonna remove this kind of practice. We're just gonna include headers that's gonna be used by our computer program, right? That's the headers for the C++ language. And then for Mpi program, we have to include one additional header. That's called mpi.h. And this header actually defines all the major functions, all the major variables that's going to be used by the Mpi library. And when you actually try to compile your code, using a specific compiler that's called Mpi C++, the compiler is going to look for this particular header file, and it will try to actually identify this particular header file on your file system, right? If you have installed the MPI library correctly on your system, the MPI C++ the compiler will be able to actually find the correct header file. Right? So for now, let's not worry too much about where the header file actually is actually located in your file system. Let's not worry about that. And we're going to use a namespace that's called the std, the standard namespace, the standard C++ namespace. That's the std standard C++ namespace. This part is identical to all the C++ codes that we have written so far, and it's not really that different. The only thing that's different so far is this particular header file. Right. And now let's try to write our main function. Let's try to write our main function. And for this particular main function, I'm gonna have some inputs. I'm gonna have command line inputs. The first command line input, the first input is argc. That's the total number of command line, the number of command line inputs. It's just a count of how many command line inputs I have. And then the second input, that's a char array basically. That's an array of char. Right. And then that's my main function. So my main function is going to take two inputs, the number of command arguments, and then an array of char pointers, basically. Right. And then it's going to return a int. It's going to return an integer. So before I actually write anything else, I'm going to return a 0, basically. That's my return value for the main function. Right. So for any kind of MPI program, it consists of a initialization step and then a finalization step. So you have to initialize the environment, and then before you actually end your program, you must finalize. You must clean up all the environment. So what's going to be the initialization step for our MPI program? It's actually quite easy. All you have to do is to call a particular function that's already being defined in the MPI namespace. Right. So the first thing we're going to write is mpi init argv. And this particular sentence basically performs the initialization step that's specific to your MPI library. So MPI is actually a namespace that's already been defined in this header file. And then you are calling a function. You're calling a function that's called init with capitalized I inside of this particular namespace. So how do you actually access a particular function in a namespace? You use two colon. The double colon is a scoping operator. It allows you to actually access a particular function name or variable name or any kind of name inside of a namespace that's already been defined for you. And this particular function takes two inputs. It takes two inputs. And these two inputs happens to be identical to the inputs that you have passed to the main function. So the first one is argc. The first input is argc. Where did you actually get the argc? You get the argc from the main function. That's the input to the main function. You just copy it over to the init function of the MPI library. And then the second input is the argv, which is also passed to your to the main function as the input. That's the argv, right? And that's pretty much the initialization function that you have to call. And then before you actually close any MPI program, you have to clean up after yourself. You have to clean up after yourself. And how do you actually do the cleanup? You by calling another MPI function. It's called finalize. Init and then finalize. The finalize doesn't have to take any kind of input. You can just give it an empty input list, right? But you still have to call this function. And the same as init, the finalize function also exists in the MPI namespace, and you have to access it by using the two colon. And it's called finalize. So for any kind of a MPI program, you have to call the init first, and then before you close your function, you have to call finalize. So let me write some comments. Initialization, right? and then clean up. Just to and inside between this initialization step and the cleanup step, you can write the logic of your function. So our logic is going to be a parallel summation, right? It's basically a parallel summation. So every every core is going to read its own input file, and then every core is going to do its own summation, and then every core is going to write out its own output file, right? So one essential concept is a unique ID for each of the different cores. So how do we actually obtain this unique ID? How do we actually obtain this unique ID? We can actually obtain it by asking the Mpi library, right? So here we're gonna call two very important Mpi functions. The first function is gonna tell each core how large the communicator actually is. Basically, how many ranks we have, how many unique IDs we have for this particular run, right? And we're gonna name the particular variable. We're gonna name it as Mpi size. That's gonna be the total number of ranks, unique ranks in our communicator, right? And this we're gonna use auto as a type. We're gonna ask the compiler to figure out what's gonna be the correct type for Mpi size, right? And then the value of Mpi size, we can obtain it by calling a specific Mpi function. Let's call it. So here, again, we are using the scoping variable to access one of the names inside of the Mpi namespace. And the name we're actually trying to access is called com world. That's the universal, that's the biggest communicator that's defined by the Mpi environment. It's called com world, right? It's basically Mpi underscore com world that we have seen on that particular PowerPoint slide. But here you are actually accessing it by using the scoping operator. You are accessing the com world communicator inside the Mpi namespace. And then once we actually have a handle to that particular communicator, we can actually call a particular function on that communicator. And that function has a name that's called get underscore size. Right? It's a capital G, so it's case sensitive. It's a get underscore size. Right? So by calling this particular function, we're getting the total number of unique IDs inside of our communicator. So we know how many processes, how many ranks are actually participating in this particular calculation. And then Mpi rank, again we are introducing another variable that we are calling it Mpi rank. You don't really have to use the Mpi rank. You can just call it rank or any kind of name. It's just a variable. It's just a variable, right? The reason I'm calling it Mpi size or Mpi rank is just to make it more explicit, make the names more explicit. It's a Mpi related variable basically. Again, we can get the unique ID for each different process by calling another function that's called Mpi get rank. So Mpi size is going to be identical. It's going to have the same value on different cores. But Mpi rank is going to be different. For different cores that's executing this particular piece of source code, Mpi rank is going to have a different value. And this kind of unique value, this kind of unique ID for different core that's executing this piece of source code is provided by this particular function. And it's called getRank. It's also a function that's defined on a communicator. That's a com world. So if you don't believe me, let's actually do a printout. Let's just print out all those different values of Mpi rank, the ID, and the size of the communicator. How many cores are actually participating in the communication? Right. Let's do a cout. Let's do a simple hello world from and then followed by MPI rank, and then followed by a space out of MPI size, and that's it. So that's gonna be our first pair program. It's basically just a hello world from MPI rank out of MPI size. What I was telling you, MPI rank is gonna be different on different cores, and then MPI size is gonna be identical. Right? Let's look at the results. Let's save the file. And then I'm gonna go back to the shell. Right? So now I am back to the shell. So you can sort of see all those input files are still there, and then I have a new source code that's called a sum_par.cpp. So here I have to compile the source code, convert it into a binary executable. So what's going to be the compiler I'm going to use, right? So if it's an ordinary C++ program, I use G++, right? But this time it's a parallel C++ program, so I use a different compiler, Mpi C++. The Mpi C++ is basically just a compiler. It's actually a wrapper around G++, right? So Mpi C++ is just like a ordinary script that's gonna call G++ inside of its own scope, and then it's gonna try to actually find all those different header files, all those different libraries that's specific to the MPI environment, and then it's gonna append all those headers, all those libraries to the G++, the sequential compiler, right? So MPI C++ is basically just a wrapper around a G++, right? And then we're gonna have to pass std equals to C++14. We're telling the G++, we're telling the G++, this option is going to be passed directly to G++, right? We're going to use the C++14 standard, and then the binary is going to be called sum par, and then the source code is going to be sum par.cpp. So now let's do another. So for some reason I don't really see my. Oh, okay, I see my binary here. That's sum_par, right? So now I have a binary. So now I have to run this binary. How do I actually run this binary on all the different cores, right? On all those different cores, instead of just using a single core like in a sequential code. How do I run it? So if you want to run a parallel program, you cannot just by executing it underneath the terminal, right? You have to use a special kind of a program that's called Mpi Run. Again, Mpi Run is a executable provided by the Mpi library. It belongs to the Mpi environment. The purpose of Mpi Run is basically to execute your binary executable on a collection of computers, on a collection of ranks, basically, right? And one of the options you have to pass to Mpi Run is just the total number of processes you want to invoke. So let's use 8, right? So that's -mp, mp number of processes. That's an option, and the parameter you want to pass to this particular option in our particular example is going to be 8. We're invoking 8 processes. We're going to run this particular executable, this binary executable sum_par on 8 processes, right, by using Mpi Run. And let's just run it. And once you start to run it, you're going to see all those outputs. It's hello world from 0, that's the rank, out of 8, that's the MPI process. That's the MPI size. So that's the MPI rank, and then that's the MPI process. And you can sort of see you have different ranks, 0, 1, 2, 3, 4, 5, 6, 7, and then out of 8. So in this particular run, you are running sum par, this particular binary executable, on 8 MPI processes, and each of those processes has a unique rank, which is basically just an integer that goes from 0 to 7. Right? And you can sort of notice that the ordering of the output is not really very specific. It's just a random random ordering. This kind of random ordering is because all those different processes are actually running the same source code at the same time, but at a slightly different speed, because the workload on each different processes may have been used by the operating system with different kinds of workload, so they have a different utilization, all those different cores. So when you actually try to run your MPI program, the same kind of workload is distributed to different processes, right? And they are going to be executed at slightly different speed. So that's why you sort of see those different outputs. The outputs not in a specific order. It's like a more like a random order, right? So now let's go back to our source code. The output that you just saw is actually coming from this particular line, right? That's this particular cout. But now let's comment it out. This is just for testing purposes, to look at what's going to be the values stored in MPI rank and MPI size. So now let's try to write the logic of our code. The first thing is that we have to sort of read the input files, and the input files for different rank actually has a different file name, right? So how do we actually handle that? So different rank actually is going to read different input files, right? So let's try to construct the file name. The file name is going to be different for different ranks. Let's introduce one variable that's called fname. We're going to call it fname, and we're going to initialize fname with the first command line argument, argv1. The first command line argument. So basically, that's the common part. To each of the different rank. If you don't remember what the input files look like, they actually named like file.0, file.1, file.2. So there is a part that's actually common to all the different files, right? That's the common part. The thing that's different is the suffix, either 0, 1, 2, 3, up to 7. That's a different part. So we're gonna store the common part in fname in this particular string, and we're gonna initialize this fname using the first command argument, right? And then we're going to try to actually construct a file name that's kind of specific to different ranks. So fname plus equal to, we're going to put the dot also inside of the suffix, and then we're going to use a specific function that's called toString mpi rank. So that's going to be our file name. A common part, and then a different part. That's going to be specific to each of the different rank. So MPI rank is actually something that's close to an integer, right? We have seen it. It's close to an integer. So get rank is going to return an integer, and then we have to sort of concatenate that particular integer to a string. And you have a intrinsic function that's provided by C++. Right? It's called a toString. It's going to convert anything to a string. So it's going to convert this MPI rank, this integer, to a string. And then we're going to concatenate it with the dot, and then the suffix is going to be concatenated to the common part of fname. And then let's take a look at what's going to be the file name. So we're going to do a cout rank. Let's print out the rank ID. So the printout is going to look like a rank followed by the rank ID, which is unique, right? And then it's going to reading, and then the fname. So by doing this kind of operation, fname should be specific to each of the different rank now, right? Let's just look at what's going to be the output. Let's try to recompile it. Let's recompile the code, and then I'm going to rerun it. So I'm seeing some kind of an error message. The reason that I'm getting those error messages is because I forgot to give it to give my binary a command argument, right? So the command argument is going to be file, right? That's the common part. That's the common part to each of the file name, right? And then if I do that, I'm going to see the correct output. So rank 0 reading file.0, rank 1 reading file.1, rank 6 reading file.6, right? So now I can go back to my source code and then continue editing my files. Okay, yeah. So it looks like my file name is correct, right? My file name is correct. So how do we actually read? How do we actually read the content of from a particular text file, right? So in C++, you read files by using a IF stream, input file stream. That's an object. That's an input file stream, and then the object is called infile. Let's just use an arbitrary name. It doesn't really matter. And then we have the file name constructed already. We can use the file name to tell C++ what file we want to sort of open. What file we want to open. If we just put fname here, it's not going to take it because the infile, the constructor of IF stream is expecting a C style character array instead of a C++ string object. So you have to sort of convert a C++ string object into a C style character array, and you have a function for doing that. It's called a C_str. So this particular function is going to convert the object, the string object, into a C style character array. And then you have to tell the constructor what kind of a mode you want to. So it's an input mode, right? And by writing this particular line, you are supposed to actually be able to open the particular file, and then connect that particular text file to an input stream. And the input stream is called in file, right? But usually you want to sort of check just to make sure that you have successfully opened that particular file. How do you actually do that check? You do a if statement. So if the file has been successfully opened, in file is not going to be null. You have a non-null value for in file. Otherwise, you're going to have a null in file. You're going to have a null value for the in file. And here we're actually testing to see if in file is null or not, right? If it's null, we're going to send something to CR error opening input file followed by the file name, end of line. And then we want to stop our execution by just doing a brute force exit. So that's a check. If the file is not successfully opened because of any kind of reason, for example, if the file doesn't actually exist, then we're going to exit the program. We're just going to do a brute force exit. For MPI programs, you actually have a different way for exiting programs. It's called Mpi abort. But for now, we are actually not using that particular function. We are just using a C function, C system function that's called exit, right? And then let's try to sort of read if our program actually passes through this particular if guard, then it means that we have successfully opened the particular file. Now we can actually read from that particular file. How do we actually read from that particular file? First of all, we're going to define a variable. We're going to define a variable auto value .00d. So we're going to define a double variable that's called a value, right? And don't forget we have more than one values inside each file. So we're going to use a vector to store a sequence of values. It's basically a vector of doubles, right? We're going to call it values. We're going to call our vector values, right? So it's plural, it's values. And again, here it's singular, it's a value, right? There's a slight difference. And then we're going to just read from our file, basically from our input stream, in file, and then we're going to use this kind of input redirection operator, this kind of thing. And then we're going to put it into value. into the double. So basically this particular sentence is gonna serve two different purposes. The first purpose is to read a double value from the input stream that's called in file that we have already opened here. And then we're going to read a double from that particular file into this particular variable that's called a value. A second thing is that this particular sentence is going to return a true or false. It's going to return a boolean, right? If the read was successful, then it's going to return a true, and this while loop is going to keep executing. It's going to keep looping. But if the input, if this particular sentence is incorrect, it's going to return a false. So once you have reached the end of the file, it's going to return a false. Once it returns a false, this while loop is going to stop executing, and we're going to jump out of the loop. And then what's going to be the body of the loop? The loop body is relatively simple. We just put the value that we have just read from the file into that particular vector by using a pushback. So values, that's the vector. That's the vector. We're going to call the pushback function on this particular vector, and then the value we're going to push it into it is the value that we just read from the file, from the input file. And once we have finished reading from the input file, don't forget to close your input file stream by calling the close function. On the file stream, and we are done. We're done with the input. So we have finished reading from the files. Right. Let's try to save it, and then let's go back to the terminal, and then let's try to compile it. So we don't have any compiler errors. Now let's try to run it. Mpi Run mp8 .sum par, and then give it one command line input. It's not giving us any runtime errors either. So we have finished reading from those different input files. So now let's try to write the compute part of our program, right? So each of the different cores are gonna do a summation. It's gonna do a summation of all those different vectors, right? That's all those different numbers that's stored inside of those vectors, right? So each of the different rank is gonna have a different vector. So the numbers that's stored in this values vector are gonna be different for different ranks, right? So the summation will be different. The summed up value, the partial summation will be different, right? How do we actually sum over all the different numbers? First, let's define a double, or we can just do an auto sum. We define a variable that's going to be used to store the partial summation, right? And then we can just do a for loop, a range for basically auto. Our iterator is going to be d, a double number, right? And then it's going to go through all the different values stored in the values vector, right? And then inside of the rank, inside of the loop, we're just going to do a accumulation, and then that's it. That's our computation. That's our computation part. That's the computation part. It's just a simple accumulation. But now let's look at let's look at the results. The results of our calculation. Let's look at the results. Let's do some output. Let's just print those numbers onto the screen. So in order to actually verify that different rank indeed has a different values vector, let's just print out the first and the last value of the last element of the values vector, right? So let's do a cout rank. So mpi rank. So I'm gonna print out the rank ID first, and then vector size. So in fact, different rank is gonna have a different vector, and all those different vectors are actually having different sizes, just because within each of the input file, different input files actually have different lengths, different number of lines basically. So different rank is going to have a different vector, and those vectors will have different sizes. All right, let's take a look at those different sizes. And then the first element, here we're going to call a specific function that's called front. So front is a member function defined on a vector. And this particular function is going to return a reference to the first element of the particular vector. And then we're going to just print out that number. Right? And then last element. And then we're going to use another function that's called back. And this back function is going to return a reference to the last element of a particular vector. Right? And then we're going to print out the sum. And then let's just take a look at those screen dumps. Let's just take a look at the screen dumps. And then let's just run it. So that's going to be, so these are our previous printout screen dumps for reading the files. Right? Here you can sort of see the output. So rank 6 vector size is 21 because if we do a wc-l and then file.6, you have 21 numbers in file.6. That's the input file for rank 6. So that's why your vector size is going to be 21 for rank 6, right? And then the first element is 0.142856, and then the last element is 3. The sum is 33. If we want to sort of double check, we can do a head in one file.6. We're just looking at the first number in file.6. That's 0.142857. 0.142857. You have additional digits in the file, but the printout has just this many digits. Some of the digits are truncated because of the precision of the output. And then that's the first element in the file. And then the last element of the file is supposed to be 3. Let's do another tail in one file.6. That's 3. So the last element in the vector for rank 6 is going to be 3. And then the summation is going to be 33. It's going to be 33. And then for a different file, for example, rank 1, right, vector size is 2 because it has just the 2 numbers. wc-l file.2 has rank 1. It's not rank 2. So wc-l file.1. So it's got 2 numbers in it. So let's get back to our source code. So that's going to be our screen dump for the output. But we would like to actually, for every different rank, to write out a particular file, a text file, so that we can store the sum that's specific to that particular rank inside of that particular file. And each rank will write out a different output file. So how we are going to do that? Right? So first, let's try to construct a rank-specific output file name. Again, string f out. We're going to use f out as our output file name, right? And then let's try to initialize it with the common part of the file name. Let's call it sum.par.out. So that's going to be the common part. That's going to be the string that's common to all the output files, right? And then we have a unique part that's specific to each of the different ranks. So f out is going to plus equal to string to underscore string mpi rank. So that's the rank specific part to our file name. So the output file name is going to look like sum underscore par dot out dot followed by the unique mpi rank that has been converted to a string and then concatenated to f out, to the common part. Right? It's not a colon, it's a semicolon. It's supposed to be a semicolon. That's going to be our output file name. Once we have an output file name, we can open a output stream that's connected to that particular file name. So output file stream is also an object that's called OF stream that's provided by C++. And then we're going to call our output stream as out file. And then we are calling the constructor of the output stream, but we must provide a file name for the output file. And the file name is fout. Again, it doesn't actually take a string object. It only takes a C-style character array. So we have to convert the string to a character array by calling C star. And then we have the output stream. So once we have the output stream, we can write to it. We can write to it by using this operator. Right. And before we actually write the numbers to it, let's try to use another function that's called set precision. So set precision is going to control how many digits we're going to see in the output file. Right? It's a double precision number. So how many digits we want to see, right? Set precision. We're gonna see like 8 digits. We're gonna specify 8 digits in our output file, and then the sum, and then end of line. So that's the only thing that we want to write to our output file. Once we have finished writing the output file, we have to remember to close it, to close the stream, and we're done. And we're done. That's it. That's it for us to actually write out the output file. Let's save the file, and then let's go back to the terminal. Let's recompile it. Now let's rerun it. And it has finished running, and we're supposed to see a bunch of output files, and indeed they are here. So there's some underscore part out dot 0, that's for the 0th rank, and then dot 1, right? So if we do just a cat sum part out question mark, we're gonna see all those different values. Those are the summations. Those are the partial summations for all the numbers in each of the different input files, right? And then if we actually try to sum up all those numbers together, if we do a cat sum, that's 8 numbers, right? That's 8 numbers. AWK s plus equal to first column, and then and print s. We're gonna see that's 83.7143. So that's doing this is a command line shell script just to actually sum up the 8 different numbers in the sum underscore part out dot question mark, or the 8 different output files generated by our parallel partial summation code, right? But if we actually try to do another summation, let's try to compare the values, right? If we just cat all the numbers in the input files, file dot question mark, and then pipe it to our summation script, are we gonna see exactly the same number? Yes, indeed, we're seeing exactly the same number, which means that our partial summation is actually correct. So just a short recap about the program we have just written, right? So this is our first parallel program. It's not really doing any kind of inter-process communication, right? There's no communication among the different ranks. All we have done is to do a partial summation. And how do we actually initialize a MPI program? We do that by calling this particular function called Mpi Init. How do we actually close down and then clean up our parallel program? By calling Mpi Finalize, right? And then how the Mpi library is actually providing a unique rank or unique ID to each of the different processes. We do that by calling the getRank on a specific communicator. That's called a com_world. How do we actually know, how does each rank actually know the size of the communicator? How many processes are actually participating in the calculation? We get that kind of We get that kind of information by doing get size. And once we have the values for those two different, once we have those values for the rank and then the value for the size, we can write our codes based on that kind of information, right? Here we're actually doing an input, where basically each of the different rank is going to read a different input file, and the file name is kind of unique to each of the different rank. We constructed that input file name by concatenating a common part. That's the first command argument to our paraprogram to the rank. So fname is going to be unique to each of the different file name, to each of the different rank, because the file name itself was constructed from this unique rank, right? And once we have finished constructing the file name, we can actually read from the input file, right? We can read from the input file, right? And that's how we can actually read from an input text file, right? Once we have finished reading that input file, we do our calculations. We do our calculations, right? We do our calculations, which is just a simple summation of the vector that we have constructed during the reading of the input file. And once our calculation is done, we have to print out the results, right? Again, the output file name is unique to each of the different rank because the output file name is also constructed from the rank ID, basically Mpi rank. That's the rank ID, which is unique to different cores, right? And then once we have the output file name, we can just open a output file stream and put this partial summation into that output stream, and then don't forget to close the output stream, and we're done with our first parallel program.